afternoon, ladies and gentlemen. It's wonderful to be here with you today. I'm going to talk about GraalVM, but allow me to introduce myself really briefly. I'm Jan Stępień. I work at InnoQ here in Berlin as a senior consultant, a whole lot with people and a little bit of computers, software development, architecture, various topics. Enough about me, let's talk about GraalVM. And we need to start with some background. When we write in our favorite JVM-based programming language, we begin with this human-friendly form, the actual code, and using the ahead-of-time compiler, translate it to JVM bytecode, this representation which is friendly towards JVM, right? But still abstract, still independent from the target computer architecture. And once we've translated it, we can either persist those files on disk or keep them in memory and execute them straight from the memory, like we do in JRuby or Clojure. Once JVM gets those class files, it starts to slowly execute them, and I mean it, very slowly. It's a slow interpretation process. And as it executes our code, it keeps track of all the important methods, all the important parts of code, which are crucial to long-term performance of our application. And then the second stage kicks in, the just-in-time compilation. And this is this tricky piece of machinery which translates this abstract representation to native code of our processor, focusing on those methods which are important in the long term, right? Those which are keep getting executed over and over again. Both of those aspects are very interesting, and we're going to invest a couple of minutes into both of those. But what I'm going to focus on at the beginning is just-in-time compilation. On the JVM, our go-to just-in-time compiler has been Hotspot. Hotspot has been around for nearly 20 years now. It's a mature and incredible piece of technology. Not only it's been maintained for nearly 20 years now, but also it evolved, it scaled with different ways we program on top of JVM, right? Java we coded 10, 15 years ago has little to do with how we write Java these days with functional interfaces, with lambdas, with immutable objects, not to mention other programming languages, right? If we code Scala, Clojure, Kotlin, the resulting bytecode is different, and yet Hotspot can optimize it and bring very satisfactory performance. Now, there are problems, right? It's a 20-year-old C++ code base with its own fair share of technical debt. And engineers behind Hotspot decided it's time to start all over again, because the cost of introducing more optimizations, new optimizations, is higher and higher. So they started again, and they did it in 2 steps. In JDK 9, they introduced this new interesting interface to JVM called JVM Compiler Interface. JVM Compiler Interface allows us to write our own just-in-time compiler and connect it to the JVM. Decouples just-in-time compilation from the virtual machine itself. And as the second step of the process, they implemented this interface using Graal. And Graal is this compiler suite, so which is capable both of just-in-time and ahead-of-time compilation. It implements this compiler interface and is language agnostic. It operates at the JVM bytecode level, and it doesn't care what languages it operates on. Now, this is Graal, and then the entire package which has been shipped recently is called GraalVM. And GraalVM is a JVM environment, the entire package, with Graal as a replacement for Hotspot. Okay, we've discussed a couple of nouns. Now let's focus on people. Who are actually the target groups of this recent development? There are 3 of them. First of all, JVM engineers, people who have worked on JVM for ages and see that it costs more and more to squeeze more and more performance from our virtual machine, from our code. Now they start anew from a green field, and they can work on Graal instead of maintaining the C++ code base. By the way, Graal itself is written in Java, so it's a just-in-time optimizer for Java written in Java. The next group are authors of programming languages, people who People like us who maybe on Saturday evening sit down and implement their own programming language. I don't know why you're laughing. Those people typically had to start by writing their own virtual machine, their own garbage collector, their own compiler. It's a massive undertaking. And Graal gives them abstractions to build on top and stand on those shoulders of giants implementing their own programming language, forgetting about all the nitty-gritty of VM, GC, just-in-time compiler, and so on. And then finally, the group which I think we represent in this room, so programmers and end users of our software. With those groups in mind, let's discuss the architecture of GraalVM. GraalVM, as we've mentioned earlier, consists primarily of those two pieces, right? JVM, we all know, plus Graal as a replacement for hotspot, communicating over this JVM CI bridge. JVM informing Graal, hey, I have this method to compile, make it quick for me. And Graal compiles it. Now, this Graal is the foundation on which Java is implemented. But it's not a particularly user-friendly interface. It still operates on the JVM bytecode level, and it's not bytecode all of us speak fluently. So on top of Graal, authors of this suite developed another abstraction called Truffle. And Truffle is the set of APIs allowing us to express semantics of our programming language in a far more user-friendly manner, expressing them as walkers of abstracts, syntax trees. And on top of this far more user-friendly representation, several programming languages have been implemented. For instance, Ruby as Truffle Ruby. It's a fascinating project. Ruby is known for being difficult to execute quickly. And so far, the state-of-the-art, to the best of my knowledge, was JRuby. Truffle Ruby improves on top of JRuby's performance massively by expressing semantics of Ruby in terms of Truffle and then executing them on Graal with all the benefits of just-in-time compilation in Graal. But that's not just one language implemented on top of Graal. Another interesting example is Sulong. Sulong is a project which implements LLVM bytecode in terms of Truffle, meaning that we can take any programming language, we can compile to LLVM bytecode, C, C++, Rust, run it on Sulong, have it executed by Truffle on Graal, and have it running natively on JVM without any native interface, with all the just-in-time optimizations. It's incredible, and it actually works. Okay, let's return to those groups. We see that JVM engineers have a far easier task, right? They start from a greenfield Java project instead of maintaining all the technical depth of the old hotspot compiler. Authors of programming languages have far friendlier, far more approachable foundations to build their programming languages atop. What about us, though? Well, we also benefit from this technology, and quite substantially. First of all, GraalVM is a polyglot environment. It doesn't care about the programming language we are running here. Graal can run Java, can run LLVM-based programming languages. It comes with implementations of Ruby, JavaScript, Python, R, and it doesn't care about language it's executing. Boundaries between programming languages just blend away on this VM. In a single VM, in a single instance, you can run several programming languages and have Graal inline functions in JavaScript into methods in Ruby. It's just fascinating. And on top of that, we have polyglot tooling, allowing us to, say, use Chrome JavaScript debuggers to debug our Python programs, or inspect memory of Ruby heap using JVM tooling, like JVisualVM. On top of that, we have faster execution, right? Thanks to the fact that authors of JVM can iterate far more quickly. They don't need to recompile the entire virtual machine to test a new just-in-time optimization. They can work on those improvements with a far shorter feedback loop. And you can already see that. GraalVM, the version you can just download from GitHub, in certain workloads is significantly, noticeably faster than off-the-shelf JVM. And then last but not least, native compilation. This is the bit I'm most excited about. As I mentioned, Graal is capable not only of ahead of time, but also not only just in time, but also ahead of time compilation. Being able to process arbitrary JVM bytecode and translate it ahead of time into a native self-contained binary for Mac, Linux, without any further JVM dependency, which brings us directly to native Java. Let's see how it works. From GitHub, we can download this 1/4 GB package, which includes entire GraalVM with implementations of several programming languages. As I mentioned, JavaScript, Python, Ruby, and so on and so forth. Plus, my favorite, the tool for natively compiling those languages. Let's write a bit of Java. Right, the simplest thing possible, a hello world printing something. If we compile it using traditional tooling and run it with JVM proper, we need a couple of milliseconds and a handful of RAM to execute it. Now, we use a native image to translate this .class file into a native binary. What it does is that it starts with our main method, and then it finds all the classes, both in our code, among our dependencies, and in JDK, performs this reachability analysis, gathers all of those classes, and translates them into native code. The results are stunning. The startup time virtually disappears, and the memory usage is significantly reduced as well. The resulting binary, hello world, doesn't have a virtual machine inside anymore, bar a small garbage collector. Okay, this was a small hello world class example, right? Typically, we write something a bit larger. So today morning, I wrote this small demo, live pre-recorded demo for you, where I wrote this tiny binary exposing a telnet interface and then being able to connect over TCP to this telnet interface. Here I'm copying the port, and in the other terminal, I will remotely connect to it to stream multimedia content. Exactly. And you're laughing, right? But think about it. To implement telnet protocol, we have to process binary data. There is communication over TCP going on. It's even responsive design. Look how it fits the entire canvas. This is enterprise software. Those are things you and me work on a daily basis. Those parts of JDK are supported and can be compiled just like that. So we have a choice now, right? We have a choice between either compiling our Java, Scala, Clojure, Kotlin as late as possible, which costs us some memory, some startup time, but we can arguably achieve higher top speed of our applications, or alternatively, we can ahead of time pre-compile our fat jars, obtaining far faster startup, reduced memory usage, but we sacrifice top speed. How much exactly? It depends on an individual benchmark. In some cases, I saw 50% slowdown of top speed. It depends. Of a just CPU, on just CPU intensive load. Okay. As exciting as this is, Java is a statically typed programming language. So we can imagine that being quite amendable to static analysis, compiling Java to native code ahead of time is not as astonishing. How about something else? How about a dynamically typed programming language, one which is in its very nature a very dynamic environment? This I would find far more exciting. So let's talk about native Clojure, a dynamic Lisp, which we can compile to JVM bytecode. And instead of a hello world, let's implement something like JQ. JQ is this lovely small utility which allows me to perform a lookup and a JSON data structure. Here I pass the path I want to look up, and I get the value under this path, and the data structure I got in the standard input. To implement a very simplistic version of JQ in Clojure, I need that much code. I hope everybody can read it. I'm sorry, it's Clojure. I hope it's fine. So what happens here? We are importing a pretty printing function from standard library to pretty print our code with indentation and everything. We read data structures expressed not in JSON, but in a Clojure native human readable serialization format. We read them from the standard input. Then we get in the data structure using a path we passed as the argument to the main function, think main method. And then we pretty print the results. 3 steps: read, lookup, print. The typical thing we would do in the Clojure world is similar to the Java approach. We compile this code to JVM bytecode and then package it as a fat jar, including both our code and all the dependencies. If we do it and then run this pretty printer to look up in this data structure a hash map with A pointing to a vector 5,3, and we try to look up path A and then first offset, we get 3 as expected. It takes us 1.5 seconds and quite a bit of RAM. Now we can improve the situation a bit. JVM is a very flexible creature. So we can pass this extra option, which I like a lot, which instructs the JVM to stop just-in-time compilation at a certain stage and don't perform any further optimizations, which allows us both to save half a second and a handful of RAM. Just to offer you a completely other execution environment to compare against, we can translate our small example into Clojure script, which is nearly the same language but targeting JavaScript engines as its execution environment. And Lumo is such an environment embedding the V8 engine, the one you know from Node or from Chrome. So we're executing exactly the same code as JavaScript, which brings another half a second of save time and a similar order of magnitude of RAM being used. Now let's introduce native image into this picture. Again, we compile with native image. It takes 2 minutes, and I can tell you it uses all the RAM it can find on your machine. And then the result is just stunning. The startup time pretty much disappears, and the memory usage is cut by 90%. Let's look at numbers again. On JVM, we need a second, 100 megs of RAM. On JavaScript, we save some time, but the memory usage is similar. It's just incredible. And those are numbers you can reproduce for various examples, various programs when it comes to their startup time and reduced memory usage. We will try to answer the question, how is that even possible? But before we do, let's think about potential applications of this exciting development. Let's talk about command line utilities. I'm a great fan of the Unix philosophy, building small self-contained tools which do one thing, do it well, and just do the work and pass its output to the next tool. Being able to compile JVM programming languages to native binaries enables us to use Java successfully in such pipelines. I'm going to show a lot of Clojure, but if you just don't know the language, don't worry. Details don't matter that much. Just translate examples to your favorite programming language, which runs on JVM. It all works the same. Let's build a small tool translating JSON to Eden. Eden is this funny Clojure human-readable serialization format you saw before. In this utility, we will depend on the JSON library, which is part of the Clojure standard library. And we will repeatedly read JSON from the standard input, one object after another. Potentially, it's an infinite stream of JSON objects. And then we will keep reading them until we hit the end of file marker, which might never happen, but infinite streams are just fine. And then we just keep printing one after another. We just run print function on those parsed JSON objects, and print by default prints them as the native Clojure human readable format called Eden. If we give it a spin by precompiling it firstly to JVM bytecode and then to native image, we can take package.json of our favorite Node.js project and then translate it to the native Clojure representation. Right? We see some similarity. Some of us have seen such shape of data. Those numbers don't surprise us anymore. OK, so we can translate JSON to another serialization format. What we can do as well. Spec Provider is a really nice project which is part of the Clojure ecosystem. In essence, you show it a lot of examples of some data, and it tries to deduce the shape of the data. It tries to give you a specification which covers all the examples, which is like the minimal description of the shape of your data. Think automatic generation of fields of classes based on exemplary data. And now, if I steal an example from the README file of this project, it looks like this. In essence, I have 3 examples of a data structure. The first one is a bit off, because under keyword C, I have a keyword, not a string. And after I infer specifications from those examples, I can print them. And after printing them, I see that the library understood the shape of the data, telling me a small map is something which has 3 keys, A, B, and C. A is an integer, B is a string, and C is a keyword or a string, which corresponds exactly to this. Now, this is what I took from the README file. Now let's package it again with a small Clojure utility. This is the most complicated piece of Clojure I'm showing today, so no worries. I'm pulling Spec Provider and some other utilities to my namespace to use them later on. And then in the main function, I keep reading data from the standard input. And I call this sequence samples. And then this sequence of samples of your data is passed to Spec Provider infer specs. And I finally print all the specs I've learned to the standard output. So on the output, I will have Clojure code, which covers all the exemplary data we saw on the standard input. Before we run it, let's add one more thing. We're printing Clojure code. So what we might add to finish off this pipeline will be a pretty printer, something which will neatly format our Clojure code for us. One such pretty printer is called zprint. Zprint is one of several pretty printers for Clojure. In this case, we don't even need to write any code or precompile anything using native image, because zprint for a number of releases now ships precompiled binaries using native image for a number of platforms. Let's write our Unix pipeline. We will take a handful of package.json files, translate JSON to Eden, to this other serialization format, then deduce all the shape of a package.json file, and pretty print format the resulting code. When we run it, in half a second, we get a specification of a package.json file expressed in terms of Clojure. Instead of starting 3 JVMs, we used 3 small command line utilities. It took us less than half a second of time. Arguably, quite a lot of memory was used. I find it excellent, right? It opens a new area we can explore with JVM-based programming languages, be it Clojure or any other of your favorites. OK, we already know that those programs can start quickly and use little RAM, but what else? What else can we, what else brings GraalVM to the table, to our tool belt? Let's talk about web applications. And in this case, I'm not interested in how quickly they start, how much memory they use. No, I'm going to talk about certain operational aspects. I want to implement this simple API. I want to be able to put something into my key value storage. For example, city is Berlin. And then I want to get it's back obtaining Berlin from the stored key. It would be lovely if stored key value pairs were persisted in the temp directory as individual key value, as individual files for each key value mapping. To implement this, I need that much code. I don't expect you to read it. It's too small and it's too much of it. All I want to show you is that we need roughly 50 lines of Clojure to connect a couple of libraries together and build a self-contained web application, including an HTTP server, which does the whole thing, including saving to the temp directory. Now, as we typically do, we compile this to JVM bytecode and then package in a fat jar. Then when we compile it again using native image to produce this self-contained binary, we're not interested in how much time it needs to start up, but rather how large the whole thing is and how well it fits into a deployment pipeline built on top of, for example, Docker images. Let's write a simple Docker image. We start with Ubuntu as our base. We pull all necessary dependencies. Liningen is a Clojure build tool. We have a couple of other things from the standard repository, plus GraalVM proper from GitHub. We add project CLJ, which is a file with all our dependencies and project configuration. We pull all the dependencies. Then we add our sources and build a so-called Uber jar, as we call it, which stands for a fat jar. And then finally, we translate the whole thing into a native image using, well, native image. And now the twist. We start again, but from scratch. We start again using the new Docker multi-stage functionality with a completely empty base image, which has not a single file on it. And we copy the main key file we obtained from the earlier stage. As a result, we end up with a Docker image which is completely empty and it has just a single file on it. Our application, our statically linked application, amounting to a total of 13 megabytes in size for the entire Docker image. Sure, it's small. It's a far smaller deployment unit to think of right now. It's also putting us in a similar league as Golang, right? Being able to build those small self-contained static binaries without any dependencies. But there's more. Think about all the things we don't have to worry about. Our Docker image has no operating system on it, has no libraries, has just our application. Think about all the things we won't need to patch if there is another security vulnerability, right? The security impact is something which I'm really excited about here. Fine. Now let's return to a question which we've asked a couple of minutes ago. How is any of this even remotely possible? Let's look at numbers again. If we think about it, we can sort of explain the memory situation. Remember that JVM and V8 both have complex, advanced, mature, just-in-time compilers, which keep statistics about the bytecode that they're executing and make informed decisions which code to optimize, run the optimizer, generate code. All this machinery has its cost, right? All this machinery has to fit and live somewhere. So we can, to a degree, explain, okay, this difference makes sense. What about the startup time? The lack of just-in-time compiler doesn't exactly explain the startup time of tiny Hello World examples. Even less so larger ones. To understand it, we have to look at the actual bytecode generated from our programs, the JVM bytecode. And here I'm going to focus on Clojure again, but I'm not going to show any Clojure code. 4 years ago, Nicolas Cariniemi wrote this excellent series of blog posts where he took various Clojure programs, compiled them to bytecode, and then decompiled them back to Java, and was looking at the resulting Java code produced from Clojure code. Clojure is known for needing a second to start up. And it turns out that most of the heavy lifting is happening in so-called static class initializers. They are those parts of Java classes which are executed when class loader loads a certain class into memory. They perform all necessary initialization, bookkeeping, all this stuff. Clojure does a whole lot of work in those static class initializers. It recreates the entire structure of namespaces. It recreates all the functions, assigns those functions to namespaces, assigns metadata to those functions. And the important thing is that GraalVM executes all the static class initializers at compile time. It runs all this code when it's processing your classes and persisting into your binary just the resulting state of the application of the class. And then when you start the thing again, you're just loading data immediately into memory and you're good to go. And Clojure in particular benefits massively from this optimization, from executing static class initializers at compile time. But other languages, Java, Kotlin, Scala, you name it, also benefit substantially. There were attempts to, for example, compile Scala C, I believe, the subset of Scala C, the Scala compiler, to native image. And savings are also massive. If you'd like to understand more, dig into details of this process, I encourage you to take a look at this blog post written by one of the team members of the GraalVM project. No need to take pictures. I posted slides already. In this post, the author explains how those static initializers work and how you can control their behavior. Because if in your static class initializer you are accessing a file or a database, this database must be available at compile time, not at runtime. So they come with certain twists. Naturally, most of the applications we write, which use databases like you normally use databases, are not affected, so don't worry about that. Okay, it's time to sum it up. We've discussed quite a lot today. We defined all the terms. What is Graal, what is hotspot, what is GraalVM, how those things fit together, why they were created, how they were structured, and who is benefiting from them, which group is actually reaping all the benefits from this new structure. Not only as programmers, we can benefit from reduced execution, from reduced startup time and increased execution speed. But also we get polyglot tooling, allowing us to mix and match languages on a single platform without any performance impact. We also can use polyglot tooling in a single environment. But the thing I find most interesting is the fact that we can finally translate JVM-based programs into native binaries, opening a completely new niche for JVM-based technology, right? We can build small command line utilities. We can build web applications, which take just a fraction of memory necessary to run them. The deployment impact, the operational impact, all the things you don't have to ship, the entire virtual machine which is not necessary. All those things, all those worries are gone with this technology. I encourage you to give it a spin. Download the thing, try it out, compile your project, see it work, see it fail, blog about it, go to a local meetup, talk about it. We would really benefit from your experience reports. My name is Stępień, and this is all I've got. Thank you all very much. You've been a wonderful audience.
We got a couple of minutes left for questions.
Hey, I have a question about, you showed like, I would say quite simple applications, like Hello World, which doesn't really depend on any library, or like a really shorthand web application, which isn't that complicated. If we move that to something like a huge Spring Boot application with tons of dependencies and stuff, how do you expect, in terms of unexpected behavior of those combinations, or even that's not building, what do you see? Is it like worth a try to move, or is it quite unstable until today?
It's a very good question. It's still a release candidate, right? The thing, so it's first RC1 in April. Now we're at 9th release candidate. So we are still not in a stable situation, right? People have been successfully using GraalVM, the just-in-time version, the thing which is a normal JVM, and using it in production, they were happy. I think Twitter was reporting running some Scala services in it, and they were happy, especially with performance. When it comes to native compilation, that's an open topic, right? Open question. It's still early. The tool, when it finds some Java construct, some certain Java API which it doesn't support. For example, dynamically loading classes at runtime. It just throws until you look like this functionality at this stack trace. I cannot do it. I cannot do it in a native binary. You can force me to compile it, and then I will throw exactly the same exception at runtime. So you can experiment, right? You can force it to compile and see what breaks and what doesn't. So it's still early days. We have to experiment, and that's why I'm encouraging you to give it a go and see how it works. For examples using Spring. Is there any other person who'd have a question? Yes, I see some questions there.
I had another one.
Let's give others a chance.
I understood that one of the big reasons to start with GraalVM was that, well, it's just easier to work with than like the legacy code base of Hotspot. But are there some things that you are doing in a completely different way? But like, for example, also different optimizations you do in Graal that you don't do in Hotspot so far?
Yes, there was something. There was it escapes me now. There was a certain optimization, whether some other form of escape analysis of objects allocated or something else. There was a particular optimizations which GraalVM folks were really proud of themselves and boasting at conferences that they were able to ship it language agnostically, works for every programming language. But I forgot it. You have to look at the sources. Check out their blog, which I showed earlier, the GraalVM blog.
In the same program, can we use multiple programming languages? And if you have a Jupyter notebook, for example, for that, I think it can be useful for prototyping.
Yes, Python is supported, so Jupyter notebooks should also work using GraalVM just fine. Or have I misunderstood your question? Sorry.
In the same Jupyter notebook, I want to use Python, Scala, and Go together.
I don't know whether Jupyter, the UI, is ready for it, but there were people mixing and matching, running some R modules for statistics in their Java code, and it just worked. So the answer is that defensive, yes.
Okay. Thanks.
Anything else?
Can you do some cross-platform compilation, for example, on Linux to build some Windows binaries with this system, like in Go?
I don't know. I was building Mac things on Mac, Linux only on Linux, and I think they have Windows support coming. Cross-compilation, I'm not sure. Sorry. There's one in the back and in the front.
Yeah, I mean, I just like literally learned about this like 5 seconds ago on my phone, but I was just looking to see if somebody was running Elastic on GraalVM, and apparently somebody was running Elastic on GraalVM. Have you heard of anybody doing anything like that? Or is that the first you've heard of it as well?
This is super exciting. I haven't. Twitter's
I mean, that's a
selection of
beast of an
Scala
application,
services.
right? So
It's just a Java app, right? It's a big Java app saving a lot of stuff on the disk and calling Lucene all the time. So it's really cool. I would love to see the numbers.
Can't tell you anything. I just learned about it now. So
super cool.
But you know.
Also Cassandra. I think Cassandra is also Java, right? It's
Yeah,
similar
so.
story. Cool. Any other questions? I saw one in the front. Yes, there. Or is there something? Sorry, with the slide I can't see anything.
It's also a compilation question. Can I compile something on my Linux machine for a Raspberry? Is this the same? Or so what I compile on Linux, would it run on the Raspberry, or is that different? native code?
It's, well, if it's the same version of Linux and same processor infrastructure, processor architecture, then yes,
No,
but I'm afraid it's not.
It's a different
It's a different one, right? So it's again, we're returning to the cross-compilation question.
Mm-hmm.
It would be a perfect fit, right? Small binary, little RAM,
Yeah,
like perfect fit.
I actually ran into this problem that I started several Java processes on the Raspberry Pi and it ate the memory.
Yeah, totally. No, sorry. I mean, I didn't research the cross-compilation story at all. Apologies. No, sorry.
Yeah.
If there are no other, there's one more. I'm trying to loop back to the first question. Asker, yes.
Probably most boring question, but what about licensing? It's Oracle. They have an enterprise version, or they at least announced one.
This is an important question, yeah, licensing. There are two models. There is the community edition, which is the only thing I experimented with so far, which you can get from GitHub. It's GPL licensed, the last time I checked, which means that, which importantly means that binaries you produce with this tool are not affected by GPL, just like GCC. If you compile your code with GCC, which in itself is GPL licensed, the resulting code is not affected by it. And there is another thing called Enterprise Edition, which comes with some extra optimizations and extra improvements, allowing you to run the thing even faster. The twist, it costs money. How much? Send them an email. You can download it and put it on trial if you just give them your email, I believe, and then you can get an evaluation version of Enterprise Edition just to be able to compare both on your workload. I hope this answers the question. Anything else? Do we have time?
No, actually the time is up.
Time is up.
Okay. Thank you very much.
Thank you very much.